Today we're happy to have Michele Galli from Humboldt-Universität Berlin to tell us about consistent truncations and KK spectrum by exceptional field theory.
Okay, so first of all, thank you very much for the opportunity to come here and speak. I would like to discuss a bit basically all the work I've been doing in the past 3 years during my PhD, mainly with my supervisor Emmanuel Malek and collaborators Henning Sandleben, Camille Eloi, and Bastian Dobrot. Right. So just for some context. Generally, since string theory requires 10 space-time dimensions, the typical question that one wants to address is what to do with the extra dimensions. And then the problem is they have to be compactified. And the problem to solve is to understand how the geometry of the extra dimensions define some lower dimensional physics, the physics of a lower dimensional theory that you want to describe. But today I would like to talk a bit about a different perspective on this, which is suppose we start from some lower dimensional theory, which is typically much simpler than the full string theory in 10 or 11 dimensions. And the problem will be to ask if we know that this lower dimensional theory comes from some string compactification. The question I'd like to address is how much information can we extract from some simpler toy model about a much more complicated theory in 10 dimensions. And the goal is to try to convince you that it's actually quite a lot of information. And I will use the tools of gauge supergravity and exceptional field theory. So everything will be in the supergravity region. So in particular, the main problems will be first to use these techniques to find solutions, because again, in general, finding solutions directly in 10 or 11 dimensions is extremely complicated. And then more specifically will be to get some to try and learn something about the ExFT and holography, and more recently about non-supersymmetric gas vacua and their stability. To find solutions, I will use mainly the tool of consistent truncations, but then to do holography, we will also need these new methods of Kaluza-Klein spectrometry in addition to consistent truncations. Okay, so I'll start by discussing consistent truncations in general and how they are constructed in this framework of ExFT. And then I will talk about two specific examples where we used these methods to study all of these different directions. Okay, so first, so consistent truncation is whenever one starts from some physical theory which involves a bunch of fields, and the truncation consists in discarding some of these fields, setting them to 0. And this process is said to be consistent whenever any solution of the reduced truncated theory is always guaranteed to uplift to a solution of the full theory that you started from. And this is the mathematical definition of consistent truncation. An example that we probably all know is when you want to do a compactification of standard gravity on a circle. This is an old Kaluza-Klein gravity. One can write a metric ansatz of this form. This is a truncation in the sense that this kind of metric only describes the dynamics of a metric on the external space, a scalar, and the potential, a one-form potential. So not every metric will have this form in general. So this is the sense in which this is a truncation. And to check that this is actually a consistent ansatz, you can plug it directly into the Einstein equations. This will give you a set of equations of motion in terms of this field. And you find that if you solve them, you're always guaranteed to also have solved automatically the Einstein equations in d+1 dimensions. But then another interesting question one could ask, so with history in mind. In particular, this was done to try and unify gravity and electromagnetism. So one could ask, can I also get rid of the scalar field? So can this be truncated? And the answer is not consistently, because if you look at the circle direction of the Einstein equations, you find an equation of motion for the scalar of this form. And in particular here, the problem is that it is sourced by the field strength of A. And so it is not consistent to set it to 0. So in general, in this example, one could simply take the ansatz, plug it into the equations of motion, and prove consistency. In general, this is very hard to do, especially for type 2 supergravity, because it involves a lot of different fields of different types that source each other in very nonlinear ways. So the way to do it is to use a symmetry argument, which roughly goes in 2 steps. The first is there will always be a group acting on all the fields, and the prescription will be to only keeping the truncation invariants under the action of the group. And what this equation says is, roughly speaking, that a singlet cannot source a non-singlet field. So an invariant cannot source a non-invariant, because you can never have a bunch of fields that are invariant under the action of this group on the right-hand side of the equation and on the left-hand side of something that is not invariant. So by choosing the fields in this way, you ensure that basically the situation I showed before of truncating the scalar cannot happen. You cannot have something that sources something that you want to keep sourcing something that you want to throw away. In particular, in this step, it is crucial that you keep only singlets and all the singlets. All the singlets have to be kept. Then the second step is more technical. Since the equations of motion will involve derivatives along the internal dimensions of the space-time, in order to ensure consistency, you will require that the derivatives of these singlet fields that you want to keep can be expanded in terms of, again, the same singlets. This is to ensure that the equations of motion factor in the end. And these two conditions can be formalized using the language of G structures. So now I will talk a bit about this. Are there any questions? Okay, so I will be schematic. All these things have proper definitions as well, but since I will not need the full power of this technology, I will try to be more schematic and do it. So first, the G structure. This will always be defined whenever you have some manifold which admits a set of tensors, specific tensors defined on it, that satisfy some algebraic relations that define them to be singlets under the action of some group. And then that group will be the G of the G structure. So a simple example that we all know is, for example, if you have a non-degenerate two-form, you have a symplectic structure, and this is because the two-form is precisely the tensor that defines the symplectic group, which the symplectic group leaves invariant. So in general, these kind of things are defined. They are topological, so they're topological questions. They're not simply algebraic, so there are abstractions to define it. And then more for the physics, now I can be more specific about what fields how one does the reduction ansatz. So if you have some field, a general field, which in general depends on both the external and internal coordinates, the prescription will be to always factor all the dependence on the internal space on these tensors here, which are the ones that define the G structure. Now, the second condition, like I said, one requires to be able to expand these the derivatives of these singlets in terms of the singlets again. And so to formalize this, you have to demand that the intrinsic torsion of the G structure is constant and singlet. So this intrinsic torsion has a specific definition, which doesn't really matter in this context. The important thing is that it's a tensor, and it's always defined in terms of derivatives of the singlets. So here derivatives means external derivatives and Lie derivatives, also combined potentially in algebraic ways as well. So, for example, going back to the symplectic case, in the symplectic case, the intrinsic torsion is exactly just the external derivative of the two forms. So, in general, demanding that this thing is constant and singlet is very restrictive. And in particular, for example, not obvious that you can do it. So, for instance, in this case, this is quite simple, but in this case, the symplectic group has no singlets in the three-form representation, and therefore the only way this can be a constant or a singlet is if it's zero. So now I'll discuss the only useful example for the scope of the presentation. So if there's one that you keep in mind, you should try to keep this one in mind. So if you have a group, suppose you have a Lie group G, you know that you can construct left invariant vector fields on the group, and that these left invariant vector fields define a global frame for the tangent bundle of G. And so then automatically they define an identity structure on the Lie group. In particular, they also have this nice property that they close into an algebra under the Lie derivative, which is isomorphic to the Lie algebra of the group itself. So these coefficients are the structural constants of G. And then you could ask in principle what the intrinsic torsion of this G structure is, and it turns out that it's precisely defined by this equation. And so it corresponds exactly to the structural constants. So in particular, the fact that it's a singlet is trivial because the group is trivial, is the identity. The group that defines the G structure is trivial. But the fact that it's constant is very non-trivial, and in fact heavily relies on the topology of the Lie group, on the fact that you're on a Lie group. It's very non-trivial. And so this will be really the punchline of the entire talk, and in particular, all the G structures I will describe are either this or a generalization of this.
So supersymmetry doesn't matter for this.
In this case, no, exactly, yes. So this is there's no supersymmetry in particular. So in this example that I'll talk about now here, you will use this to do to construct a Schwartz compactification. So it's just gravity, there's no SUSY. Yes. SUSY, but SUSY will play a role later in the supergravity things. Yes. So yes, like anticipated, you can use that G structure on Lie groups to write a generalization of Kaluza-Klein gravity, which is typically called the Schwartz compactification, where you precisely follow the prescription. You factorize you always write the metric. So you want to do a compactification of gravity on the Lie group, and you always write the metric by factorizing all the dependence on G into these left invariant objects. So in this case, these left invariant one forms. And here you see that, for instance, this is the internal part of the metric, and this matrix will contain all the scalar fields in the lower dimensional theory. So the generalization of these identity structures will play a special role in ExFT, because it will give consistent truncate, it will define consistent truncations which preserve maximum supersymmetry. And then in general, again, an important point for all these methods is that having this identity structure is very powerful. It restricts the geometry and it allows you to do lots of things. So now I'd like to talk a bit more specifically about exceptional field theory, and I'll start by trying to motivate what the grand goal of this technology is. So I'll do it with this example. Suppose you have a theory which involves a metric, so gravity, a scalar field, and a gauge potential, exactly like the Kaluza-Klein situation. It turns out that you can construct in D+, and you are in D+2 dimensions. So it turns out that you can construct a consistent truncation on a two-sphere, which takes you to a D-dimensional theory, which will be gravity, a bunch of gauge potentials in the action of in the adjoint of the group SU2, and some scalar fields. This consistent truncation, in order to do it, what you need to do is basically make an educated guess for an ansatz, just like in the Kaluza-Klein case. plug it explicitly into the equations of motion, and check directly for consistency. And it's the fact that it works is quite miraculous. It's not obvious why it works. And in particular, it only works if you tune the coupling of this scalar field phi to a specific number, how it couples to the electromagnetic field. And so it's not clear that this consistent truncation arises from a symmetry principle. But it turns out that there is in fact a symmetry principle behind this. But to see it, you have to realize that this is exactly these are exactly the fields that come from a Kaluza-Klein reduction of gravity in one higher dimension on a circle. So what you need to do is basically take all these different fields and work this direction backwards, reorganize them together into a metric in d+3 dimensions. So some kind of higher geometrical space. And then you find that from d+3 dimensions, if you do a Shirk-Schwarz reduction on the 3-sphere, which is the group SU2, you get exactly the same theory in d dimensions. And so the G structure behind this consistent truncation is really this identity structure that I described earlier. And what you're doing is really just a Shirk-Schwarz reduction, but the only way to see it is to go one dimension higher and reorganize these fields into a larger object. And so this is what exceptional field theory attempts to always, well, not what attempts, what it does. Exceptional field theory takes the fields of type 2 supergravity and 11D supergravity and reorganizes them into some larger geometrical spaces, which are the place where the G structures that define consistent truncations naturally live. And so it makes it possible to understand what symmetry principles are behind these consistent truncations.
So in this
Yes.
example, coming down on the S1, down to the S2, you're allowing monopole charge for the.
Yes, exactly. So you in particular, you would see from this path that the vibration is not trivial.
Yeah.
Yes,
Yeah.
you would see it. You would see it exactly, because if you integrate the flux on the S2, you don't get zero. Yeah. So you could compute the Chern number, for example, of the vibration, and find that it's not zero. It's not a trivial.
So isn't this way more general? Like other classes of solutions that you would get. Oh, I see. You say you want to start with the d-dimensional SU2 and then rebuild. Right. That's the.
Sorry.
Should I think of this as you want to start with the d-dimensional theory, its field content, and then reconstruct your d+3 dimensional theory from this?
No. So
Well, you're not thinking of it this way.
No. I think the point of this should be that, suppose you're here.
Yeah.
And you want to understand how to go here. If you go directly from the S2,
yeah,
it's kind of a miracle, because it's not a very systematic thing. You see that it works, but you have to work very hard, and there's no principle behind it. Whereas, the thing is, from here, if you look at it from this d+3 dimensional point of view,
yeah,
and it's clear what you're doing, because you're clearly just doing a reduction on a group. And there's a theorem which tells you why the truncation is consistent. So it's the point is you have much better control over what you're doing if you work here than if you go directly from here. And so in particular, if you construct truncations using this system, so using these G structures, you can do a lot more. You can. Because you have better control over it, and you understand essentially why the consistency is ensured. Whereas if you were to always proceed this way by just plugging the ansatz and checking for consistency, basically you'd have to case by case always do the procedure. And in particular, if you do it, this is a relatively simple system, so you can do it. But if you hope to do that for, say, type 2B supergravity, it's pretty much impossible.
Good.
So this is just like a motivation. Now I'll explain in more detail how this reorganization works. So here, like I said, I'd like to just show how this, what these fields get reorganized into. So how this reorganization goes. So on the left, I have the S2 example, and here I chose 11D supergravity written in an n plus d split, where d is the internal dimension. And so the point is that there will be an enhancement of group that these fields naturally. So these fields will be acted on by a larger group than the naive GLD that you would expect from them being differential forms. So on the left-hand side, this is the situation with the 2-sphere and the 3-sphere. Here you have, if you look at the internal directions, so these started from being things in D+2, so they were GL2 objects, and they become GL3 objects. Similarly, their infinitesimal gauge transformations get combined into just vector fields in 3 dimensions that parameterize diffeomorphisms in three dimensions. And similarly, the differential operators also that define the algebra of these gauge transformations get combined into a single bigger differential operator, which is just the Lie derivative in 3D. And then finally, the internal degrees of freedom parameterize this metric, this Riemannian metric Hij that I wrote earlier, which parameterizes the coset space GL3 divided by O3. So for type 2 and 11D supergravity, a very similar thing will happen, but you will start from something which is naturally GLD. There are naturally GLD representations, and they will organize themselves into EDD representations, where EDD is this exceptional group. And then similarly, the gauge transformations will be all packaged together into some objects which we typically call generalized diffeomorphism, generalized vector fields, that are sections of a larger vector bundle, E, which is essentially a sum of tensor powers of tangent bundle and cotangent bundle. And finally, also the differential operators that define the algebra get combined into a generalized Lie derivative, which acts along sections of E. And then again, all the internal degrees of freedom of the theory parameterize a Riemannian metric on E, which again is an element of the coset space EDD divided by the maximal compact subgroup HD. And this will be quite important actually for one of the examples. To see the action, so to see how this EDD appears, it kind of appears quite magically. The simplest way is to do this counting argument. So again, here there's the 2-sphere and the 3-sphere, what happens in that toy example. And here I have 11-dimensional supergravity in a 5+6 split. So I expect to see the group E66 just coming out naturally. So you can count the degrees of freedom on the external space. So for example, here you want to count the number of 1 forms that you get on the external space. You get 2 from the metric and 1 from the gauge potential. So this is 3, and the 3-dimensional representation of GL3 breaks as 2 + 1, matching this count. And if you count the internal degrees of freedom, you find 3 from the metric, 2 from this, and 1 from the scalar, which gives you 6. That adds up exactly to the dimension of this coset space. So for 11D supergravity, remarkably, you get a very similar thing. So if you count the 1 forms, you get 6 from the metric. So remember, I goes from 1 to 6 and mu from 1 to 5. Sorry, it's like a 5D thing, and this is 1 to 5, and this is if you want 6 to 11. But so if you count the 1 forms, you find 6 from the metric, 15 from the 3 form, and another 6 from the 6 form. This adds up to 27, and the 27-dimensional representation of E66 breaks exactly as 1 copy of the 15 and 2 copies of the 6 under the group SL6, which matches again this count. And then finally, if you count the internal degrees of freedom, you find 21 from the metric, 20 from this, and 1 from the 6 form, which adds up to 42, which again matches the dimension of this coset space. So this hides out of details under the rug, a lot of field redefinitions, etc. But the thing to keep in mind is that these exceptional groups arise naturally when you try to write supergravity in this split. And they organize themselves into EDD reps very natural, the fields. And so the prescription, the general method to construct consistent truncations in this framework will be to find a compactification that admits a G structure on this vector bundle E. And then to impose the consistency, you have to demand that the intrinsic torsion of the G structure is constant. In particular, since I will only do these generalized identity structures, the only condition that there will be to check is that the algebra now under the generalized Lie derivative of the frames that define the identity structure have as coefficients some constants. So this will be the only requirement to have consistent truncations that come from an identity structure and preserve maximum supersymmetry. And so then a useful fact for all the examples that I'll discuss is that, in fact, it has been proven that spheres always admit this generalized identity structure, and this was used to prove the consistency of several truncations. In particular, so for example, going back to your question earlier, this was suspected for a very long time that the truncation was consistent, but the proof comes from this kind of method. And it was only done in 2015, because it exactly gives you really a proof of the consistency. Okay, are there any questions? So I'll move on to the first example. So we use these methods to construct a consistent truncation of type 2b on S3 times S3 times S1. And then we study a lot of solutions, their moduli space, and we found some interesting results. So first I'll start by saying that in 2022, we worked out how to use ExFT to construct consistent truncations to 3 dimensions. But then we found that, unfortunately, unlike in higher dimensions, there is no maximally supersymmetric truncation on the 8th sphere. And although you can construct maximally, and we did construct maximally supersymmetric truncations of both 2a and 2b on the 7th sphere, we found that they were not terribly interesting because they didn't have vacua. So another interesting, solution, class of solutions that one might want to study is associated to this ADS3 times S3 times S3 times S1, very old, famous vacuum of type 2b. This is really interesting for its own reasons, like integrability and the worldsheet description and so on. And the goal was to try and understand if we can deform this solution, find a new class of vacua, and then study them, see if we can find some non-supersymmetric points, understand the moduli space, and so on, using these methods. And so to do it, you need, again, it goes in 3 steps. The first is to construct the truncation. The truncation gives you a 3D theory, which you can study, and it's much simpler than type 2b supergravity. You can find solutions there and study them, and then you can use exceptional field theory to uplift the results to 10 dimensions. Okay, so first I'll discuss how the truncation is built. So this is a product of spheres, and so we can in fact use this result that spheres are generalized, admit this generalized identity structure. And it was proven in the context of 4-dimensional truncation that this extends to products. So we can use it. And in order to construct the consistent truncation, we start from type 2b. We construct a truncation on S3 times S3 to 4 dimensions. This amounts to embedding an element of the group SL4 squared into E7. And then the second step is you do another circle reduction to go to 3 dimensions, which again involves embedding the element of E7, E7,7 that you got from there into the larger group E8,8. So you end up with a theory in 3D. The problem is that this doesn't quite work, it's not sufficient. You can see that this kind of thing will not work by looking at the vacuum solution, is the known one. And you see that there is this, if you look at the 3-form flux, there is this red term. So this is a 3-form with 3 legs on the ADS. So its dual will be a 7-form with all 7 legs on the compactification. And so in particular, the potential of a flux like this will be a 6-form with all legs on the compactification. And so this is not captured by the 4D truncation on S3 times S3. This has to be turned on by hand. And in ExFT, there's actually a very nice method to turn on this, to include this flux, which is to twist the frame of the previous consistent truncation that comes from the chain of embeddings. So remember earlier I said that these, so here we have to turn on a 6 form of the compactification. So like I said earlier, these fields with legs on the internal space, they live in the algebra because they parameterize the coset space, EDD divided by HD. So what we do is we look for an element of the algebra of the exceptional group which corresponds to this 6 form. We exponentiate it and then we twist the frame that defines the identity structure. This, of course, is still a frame, but you need to impose the intrinsic torsion condition. The Lie derivative deforms in a very nice way. The first term is essentially the old coefficients of the previous truncation, multiplying now the twisted frame. And the second term has these untwisted frames acting on some tensor, HPQ, This tensor is essentially the 7-form flux embedded in E8 in a funky way. And so you see from this equation that in order to ensure that this ends up being a constant times the twisted U, you have to impose that these old untwisted frames stabilize whatever this tensor is. And so that this tensor is a singlet under the group SL4 times SL4. So remember that the original frames were elements of the group SL4 squared. And so indeed, this amounts to requiring that the C6 that we turned on, which is an element of the algebra, is singlet under the group SL4 times SL4. This turns out to be the case, and in fact it works. And then we can check that at the origin, so at this point where the spheres are round, we recover the correct vacuum. So this tells you that you're not in the right theory, in the right 3D theory.
Does it matter which H you pick?
No, in theory, no. So for example, we picked the simplest one where we chose you can show that you can choose the gauge so that basically all this C6 essentially looks like Z, which is the circle coordinate, times some C6 with legs on the S3 times S3. Yeah. So you can you can show that you can choose it this way. Yeah. Okay, so now the consistent truncation gives you the 3D theory, and now you can find solutions directly in 3 dimensions, and then uplift them later to 10D. So the specific 3D supergravity that you get is not so important. It has n equals to 16 supersymmetry, but the most important point is that it has a scalar potential, which looks like this. So here X is essentially the intrinsic torsion from the previous equations. Eta is just an E8 tensor, and M is the object that contains the scalars. So to find the vacua in this theory, all you need to do is extremize this, so vary this potential, vary M in this potential, and then try to deform the background value of M that you had by setting the spheres to be round, deforming this M by some elements of E8, and seeing if the variation of the potential keeps vanishing. So this ensures that you're at a vacuum. So basically, all you need to do is find extrema of this potential, and by varying M. And in fact, you can do it and find a huge number of moduli, which is unexpected. And in particular, I will show you the nastiest one. So this is an example of something we found like this. And this is a metric on S3, well, ADS3 times S3 times S3 times S1, which is a solution of the Einstein equations in 10D for any value of these parameters, of these 7 parameters. So you see that, I mean, this is not terribly interesting solution, but the point is that this is the power of this kind of formalism, that it would be impossible to find this in 10 dimensions directly. But the point is that by just extremizing a potential in 3D, you can then uplift the solutions and just read off what the corresponding metric looks like in 10 dimensions.
So a bunch of these 7 parameters are squashing the
Yes.
spheres, and then some mixing, maybe of tangent bundles, mixing with the circle as well.
Yes. And
Does this include AES3 solutions that would have been warped over the internal space?
interesting. So we didn't find any warping, any solutions with a warp factor, but I think in principle you could. So you can include warp factors.
You could include one.
Yes, you can. You can. We didn't, but you can. Yes.
So in this answer, was that an output of the extremizing the potential, or?
Yeah. So basically, the potential just essentially looks like something. You extremize it. You find that for all these values. So remember that this m, essentially this m, when you go to 10 dimensions, looks like this. And it contains, in particular, remember these indices are now EDD, but they contain all the information about the forms. So what you can do is, for example, if you do MIJ, where these are like the internal indices, this you can show that it's actually just the inverse metric. And so what we do is we essentially do this, compute this M object, and then to do the uplift formulas, you only read off what the results are. So this is what we did. We took this M, we looked at this component, and we found the G.
No, I see. But just make sure I understand this one point. If you had changed, excuse me, if you allowed a warp factor, would the potential have changed, or would it be the same? I was wondering whether it fits in the answer from reducing on S3 because S3, and then doing the S1 reduction. You got the twist that puts in the flux in space-time, but
yeah, I understand. So I'm not sure exactly how the potential would change if you wanted to include warp factors. I'm not sure. I would guess it does, but I'm not 100% sure how it changes. Yeah. So I know it can be done, but I've never done it, and but I'm not sure how it would. Change. There was another question.
Yeah, I was going to say if like you had less supersymmetry, this would still work.
Yeah, so you can do it still with less SUSY as well, but basically it's a bit different because you don't have a frame. So the thing you do is essentially the same thing, but everything changes a little bit. So for example, this potential would look different. It wouldn't look like this, it would be completely different because you'd have a 3D supergravity, which has less supersymmetry, is not n equals to 16. So this isn't fixed, it's different. And then, but then what you do is essentially the same. Yes. So you can do it.
So you could still explicitly compute the solution like
yes, you do exactly the same thing. You still have this object, this M. It's slightly different. It's a little bit more complicated to construct this M, but you still have it, and you can still read off all the fields like this.
right. When you say less supersymmetry, you say reduce on something that breaks more SUSY, or start with a theory with less SUSY?
I was going to say the first one, the one with the geometry is different.
The geometry, okay.
Yeah.
Sure, yeah.
Okay, so this is actually also a good point. So there's a difference between the SUSY that the solutions preserve and the SUSY that the theory has.
Yeah.
So actually, in this framework, you can break all supersymmetry. The solutions can break all supersymmetry. The place where it changes a lot is where the theory is less supersymmetric. But in particular, so I will talk about some examples that have n equals to 0. So the vacua can break the SUSY, but this is another good thing about this technology, which is that it doesn't really care about the SUSY that the solutions preserve. The place where it really changes is when you start constructing theories that have less supersymmetry. So yeah, I mean, even this deformation in general breaks all supersymmetry. This n equals 0. Okay, so now I'd like to talk about more interesting deformation. So this is a bit simpler and more practical. In 10 dimensions, this is another deformation that we found in 3D. And when you uplift to 10D, you find that it behaves in this nice way. Essentially, it corresponds to taking always the angles that parameterize the three spheres and shifting them by the circle direction times a coefficient. And the coefficient is now the modulus. There are 4 of them. And for generic values of the chi's, this is again, in general, non-supersymmetric. But then you find that when you identify the chi's in some specific ways, there are some supersymmetry enhancements. So you have a moduli space, which is non-supersymmetric, but contains some supersymmetric hypersurfaces. And the particularly interesting point is that the SUSY families are continuously connected to the non-SUSY vacuum. And so the interesting thing here to study is, first of all, the topology of this moduli space, see if we can say something about it. And second, how the continuous limit affects the stability of the non-supersymmetric solutions.
So
Yes.
is it for the non-SUSY, once you deform away from this, from preserving any SUSY, is it obvious you don't get a tachyon at the BF bound, below the BF bound?
Exactly, so not obvious at all, but the good thing is that you can compute the spectrum explicitly and find that, in fact, you will find that it doesn't, these are stable.
Wait a minute, so how much of the spectrum can you control?
So you can compute the full spectrum in type 2B.
So the full KK spectrum.
The full KK
becomes
spectrum, yes. Yes.
I see. Okay. Oh, very good. Okay.
Yeah. And so this is in particular what I would do. So again, so this is exactly this leads directly to the question. Basically, in order to study any of this, you need to understand the full spectrum. The reason why you need the full spectrum is that essentially things can look good in 3 dimensions, but they can go wrong once you look at fluctuations in 10D. And so to see this, I have this toy example. So suppose you have 2 scalar fields with this potential. There's a consistent truncation here because there's a Z2 symmetry where you leave phi alone and you flip the sign of psi. So by the symmetry principle, you can truncate the non-singlet away. And so it is consistent to drop psi. And then you find that in the reduced theory, there's a vacuum at phi is equal to 0. And if you compute the fluctuations along this phi direction, you find that they have positive mass squared, if you want. And so everything appears okay. But then if you look at the vacuum in the full theory with both scalars, you find that the fluctuations along psi actually have negative mass squared. And so you're not really at an honest minimum of the potential. And indeed, this is the situation. You see, if you only keep phi, you look like you're at a minimum. Then once you go to the full theory and you do perturbations along psi, you find that really you're at a saddle. And so this breaks. And the same thing can happen in supergravity. In particular, supergravities are extremely complicated, so pretty much anything can happen. But then in general, it's very hard to compute the spectrum in 10 dimensions again, because typically one has to, the supergravity theories involve forms and metric. And so whenever you do a fluctuation ansatz, you have to perturb all the different differential forms. You get some mass operators, but then diagonalizing them is very complex. It's very complicated. And in general, you can only do it in some restrictive examples, like on coset spaces, where you have a lot of symmetry. So the thing that exceptional field theory buys you is precisely this. So it kills this mixing of all the various form degrees of freedom. Because, so the point is that you're always able to compute the full KK spectrum around any background, which has one of those, which has a generalized identity structure. So of the type that I described earlier with this frame. And the reason why you can do it is that you see here, if you start from some background, then you can consider fluctuations around it, but you encode all the tensor structure of the fluctuations in the frame that defines the identity structure. And so the fluctuations are really expanded as coefficients. And so they are only expanded in terms of scalar harmonics on the compactification. You don't need the full tensor harmonics anymore. You can expand the fluctuations in terms of scalar harmonics. And so then this mixing of all the different tensor structures doesn't happen anymore. And this is the huge simplification that ExFT buys you, and it uses this identity structure. So the result is that, so now, okay, I want to explain this red statement. Basically, here I only said that you need a generalized identity structure. So in particular, this doesn't care about the intrinsic torsion. Unlike the consistent truncation, this does not, you don't need to require that the intrinsic torsion of this identity structure is constant and singlet. So in particular, in the second example that I'll talk about, there will be a background which admits an identity structure, is associated to an identity structure, but which does not have constant and singlet intrinsic torsion, but will still be able to apply the spectrometry. In this case, however, for the S3 times S3 times S1, we're in a maximally supersymmetric truncation, and so we will not use this so much. We're in a simpler situation, if you want. So you can do it and then find some nice results. In particular, you find that, exactly like we were saying, the non-supersymmetric solutions are all stable within the full 2B supergravity. And another nice feature is that when you compute the spectrum of this sky deformation, if you look at the 3D spectrum, so the spectrum of the fields that you keep in 3 dimensions, it doesn't have any specific pattern. But once you look at the higher modes, you find that some higher modes become light, and the spectrum maps into himself with a periodicity under this periodicity of basically, if you shift the chi's by these integers by these integer multiples, you find that the spectrum maps into itself. And so this is evidence that the moduli space is actually compact, and you cannot see it by simply restricting to the 3D fields.
In the original, I can't remember that. In the original Brighton Logan Friedman paper, they showed you always had the tachyon can never be lower than their BF bound.
Yeah.
If it was, the background have to be supersymmetric, or just the theory had to be supersymmetric?
I think
must be the background.
The background, exactly. Yeah. I think the background.
It kind of interested. So here, even with the non-SUSY ones, you automatically get nothing lower than the BF bound.
Yes, exactly. But so yes, exactly. And in particular, I mean, in a way, this is connected to the fact that this can be understood in a way because of this limit. So it's like you say, the SUSY vacua are protected. Yeah. But here, the non-SUSY solutions are actually connected.
Yeah, smoothly connected, you say, to the.
Yes, continuously connected. But here you can check the BF bound explicitly because you compute really the spectrum, the numbers. Yeah. Yeah, and you can compute it. In particular, this calculation is analytic. So you really have some expressions in terms of these guys.
And you say the moduli space is compact, which is weird. Wouldn't have expected naively that to be true. Can you think of it as modding by some discrete subgroup of your? So
it looks a bit like exactly this kind of SL2 action on some kind of torus complex structures. Is this what you mean? Yeah. So it's similar, but I think it's a bit strange because, for example, if you think about it, so you can think about it in that way, but there's a problem with, so this is generated by the T and S transformations, right? So the T is like a shift down or something, but well, let's say K. But the S transformation is like tau plus 1. But the S transformation is like 1 over tau. And so the problem is that you go out of the supergravity regime. And so you don't see the full you don't see the full SL2.
You're seeing the shift symmetries.
Yes, this you see, yes, exactly. So the shift symmetry you can really compute and see. This, no.
Can you compute a metric on the moduli space or have some idea?
Yes, we actually have an expression. I didn't put it here, but.
Do you know what the curvature looks like? Is it positive or negative? It should be
I don't
negative,
remember.
presumably.
I don't remember. Yeah.
Mm.
I don't actually think we computed explicitly, not the curvature, I mean, the metric, yes, but not the curvature. But we can look at it later if you want, because it's there. Yeah, you can compute it. And now just to quickly recap, all these things are very nice, but in particular, this example was very useful to show that whenever you have this this identity structure with a constant intrinsic torsion is very restrictive, and it allows you to do all sorts of calculations because these symmetry principles drastically simplify all the calculations that you need to do. But now I'd like to discuss an example where we push it slightly beyond this situation and we don't have maximum supersymmetry anymore. So this is a situation where we found a domain wall solution in 11 dimensions, in 11-dimensional supergravity compactified on the 7th sphere. So the context is this holographic renormalization. So the holographic renormalization relates a domain wall solution which interpolates between different ADS vacua to an RG flow between the dual CFTs. And so the goal is to use the supergravity methods to compute something about, to learn something about the RG flow. In particular, to compute two-point functions along the RG flow. So the two vacua that you interpolate between will be an ADS4 times a squash 7 sphere, which preserves n equal 1 supersymmetry, and an ADS4 times a round sphere, which preserves n equal to 8 supersymmetry. These are very old solutions. And in particular, I will work in a truncation, which preserves n equal 1 SUSY in 4 dimensions, and it allows to work in 4D with only 2 scalar fields. And the crucial point about this truncation, where this example is different from the previous one, is that the n equal 1 truncation is not a subtruncation of the famous n equal to 8 consistent truncation that this vacuum belongs to. It's a different consistent truncation. Yeah. So finding the solution is something that you can do in 4 dimensions. So you can solve the Einstein equations with this domain wall ansatz. And in particular, the flow is non-supersymmetric. And so we solved the equations numerically. And we found that by looking at the asymptotics near the UV point, that it's triggered by a relevant operator dual to the field B. And then if you do the uplift, so this thing we were saying earlier, you can see that this is what the metric on the sphere looks like. And in particular, it's quite nice because you see that the 2 scalar fields are exactly the modes that control the squashing of the sphere. And so you start from the squash point and then you flow to the round. So this is the profile of the scalars. And this is the actual flow. So that's the potential, and the red point is the squash sphere, and the round point is the green point is the round one. And the blue line is exactly the flow. So here's where the red remark from earlier applies. So here we're working in a truncation which is n equals to 1. But the 7th sphere still admits an identity structure. And to apply the spectrometry, although this 4-dimensional consistent truncation does not come from the identity structure on the 7th sphere, you can still use the identity structure on the 7th sphere to compute the spectrum around these backgrounds, and in particular around the domain wall background. And so we can do it. We can, like I showed in the previous equation, you can take the background solution, perturb it by adding some fluctuations, And then if you plug your the ansatz into the exceptional field theory action, that spits out for you a nice 4D looking action, which has this kind of potential. So here, this is the background, and these are the KK fluctuations. And this shows you essentially a kind of effective potential with all the quadratic couplings of the fluctuations to the background. So in principle, this allows you to compute the 2-point functions along the entire RG flow. And it allows you to also do, maybe I should point out that, so I say effective because it looks 4D. Of course, this is not an effective theory in the energy sense. It's just a 4D looking potential, if you want. And so from this, we can in particular see, for example, by looking at the symmetries. So say this red field, this is really 3, 4, 5 means that this is phi 3 plus phi 4 plus, thanks, phi 3 plus phi 4 plus phi 5. And this is the only combination of these three fields that appears. And so you see that only only one of them will be physical and 2 of them will be Goldstone. And so you can see that 2 out of these 3 fluctuations will be Goldstones along the entire flow. And you can see also some other nice patterns. For example, if you look at the UV point, and you freeze the value of the scalars at that point, you find that this phi 1 also drops out of the potential. And so this phi 1 is a Goldstone at the squash point, but then becomes physical along the flow. And you can see all these nice things.
So the gravity solution itself is weak curvature throughout the flow, but there's no high curvature showing up as you go.
So you mean singularities?
Well, not anything, but even just the curvature in Planck units stays long all the way through. Like you can trust supergravity.
So it's a supergravity, yes.
Yeah.
It's in supergravity, yes.
There's no. So if you can, if you get a result of the 2-point function throughout the flow, do you have a field theory understanding of why that was possible?
So you mean, I think that one of the complicated things in this, kind of annoying things in this example specifically is that the field theory dual to the squashed, dual to the UV point is not really known, I think, explicitly. So for example, I don't think you can write down what the operator is. So you can identify with the asymptotic expansion that it's dual to V.
There's no uniqueness in the sense that there's one relevant operator. Like there's many possible flows you could have done from the.
You mean if there are several possible flows? Yeah. Okay, so this is also, so this flow is USP4 times SU2 invariant. So it has this symmetry.
Oh yeah, okay.
And it's non-supersymmetric. So you can show in particular that basically there cannot be a supersymmetric flow which is USP4 times SU2 invariant. But in principle, there could be a supersymmetric flow in general, in 11D.
No, I think what I'm wondering is you're able to get a result for the 2-point function.
Yes.
Which is somehow telling you about things that are hard to compute in the field theory, right? I mean,
yes.
Other than perturbation around the conformal fixed point,
Yes.
you wouldn't know a lot about the
Yes.
2-point function.
Yes.
Except at the endpoints. And is there a symmetry? I'm just wondering whether the symmetry principles you use here could be elevated to some statement in conformal field theory.
Okay, I see what you mean.
So you could control the flow. Like, is there a differential equation that the flow should obey and one should have?
Yes, this is actually, so this is, I think, this is basically an ongoing long-term project of everybody in this field. So in particular, what would be nice is to go beyond the 2-point couplings, because you should see some non-trivial structure in the endpoint functions in the CFT. And in principle, you should be able to make, for example, some group theoretic arguments for why an infinite number of endpoint functions in the CFT vanish.
Yeah.
So yes, so you, in principle, yes. And in particular, I mean, we're working on it. Yes. So you can indeed make some very non-trivial statements about the CFT from essentially the group theory of these that controls these supergravity solutions. Yes. So, okay, I don't have so much time, I think 30 seconds, but okay, this is the last slide. So the point of this was that we managed to push the spectrometry beyond the maximally supersymmetric truncations. We only need the generalized identity structure. We found a numerical solution for the flow. And so, okay, this is maybe more towards the future. We can now make some very concrete statements about the CFTs, the dual CFTs. So now I'll just talk about some outlook. So here, okay, here I wrote 3-point functions regarding what we were discussing, we were saying a second ago. But I mean, in general, doing endpoint functions conceptually is not any different from 2-point functions in this context, because you have the, say, when you do the KK fluctuation ansatz, you just expand to a higher order, and then you keep higher orders in the fluctuation expansion. And so in principle, you can make statements about endpoint functions in general. And in particular, like you say, is the group theory that really controls them. And it's something that you can't really see from the CFT side. So this is one general direction. Another interesting general future direction is trying to understand, again, up to now, I mean, the first full analytic spectrum around a non-SUSY vacuum was found, I think, in 2019, again, using these methods. So this is a very new thing, that these things first of all exist, and second, that much less so that you can compute the spectrum. And it would be nice to be able to make some general statements, again, maybe using group theory or using this structure of the consistent truncation, about when, if you give me some non-SUSY vacuum, can I say something about when is it going to be stable or when it's not going to be stable, more analytically, rather than just simply computing every time the spectrum and just finding that nothing goes below the BF bound. And then another interesting direction, for example, would be to try and incorporate alpha prime corrections to see how alpha prime corrections, for instance, could affect the stability of some of these non-SUSY solutions. But this is very hard. Right. Well, that's it. Thank you very much.
In your first example,
Yeah.
because you have the full KK spectrum,
Yes.
you could, in principle, add the one loop potential with a cutoff, with some kind of UV cutoff, and see whether or not it wants to flow back to the supersymmetric points or what happens. Because I mean, there's some intuition that just to fall away from the supersymmetric point, it should flow back. And it's in principle computable now.